Hey there, algebra or geometry students. We started Unit 2 last time with inductive reasoning, making conjectures or hypotheses based on previous data. Today we will continue with this kind of introduction to logic, talking about conditional statements. Conditional statements are also known as if-then statements, for an obvious reason that you'll see in a second. An if-then statement is in two parts. We say if P, then Q. So regardless of the argument that's being made, P is the hypothesis and Q is the conclusion. So I mean, these are just variables like you would use variables in algebra. They stand for any argument. So you'd say if I eat pancakes, then my son will fly to the moon. Conditional statements can be true or false. It really doesn't matter. Okay, but the structure of the statement is what matters. And the key parts are, we have an if part for the hypothesis and a then part for a conclusion. In logic, we have our own set of symbols, and so you will notice we have this as something that refers to the same thing. So this is if P, then Q. Just for this kind of vocabulary time here, we'll just go ahead and use P and Q as our generalities for a conditional statement. Save ourselves some writing. Okay. So the converse of a conditional statement is basically just the opposite. It'd be if Q, then P. So if my original conditional statement was if I love math, then I will get an A, my converse would be if I get an A, then I love math. Okay, and again, sometimes your conditional statement could be true and your converse false, or they could both be true or they could both be false. We'll actually look more into that later when we talk about truth tables. So this would be in the form if Q, P. Okay? The inverse, you're actually going to keep them in the same order, but you're going to negate both of them. So the negation symbol is this little squiggly line right here, like the top of a congruent symbol, and it just basically means the opposite. A lot of times we use the phrase not. It seems a little weird, but it fits in there most of the time. Okay, and so if we're sticking with our if P then Q, this would be if not P, then not Q. Or if we're using our logic symbol, if not P, then not Q. Right? So if I don't love math, then I won't get an A, would be a way that we say it. The contrapositive is the logical equivalent to our conditional statement. Later on we will show if the conditional statement is true, then the contrapositive is true, and if the conditional statement is false, then the contrapositive will also be false. But for right now, we'll just take that for granted. The contrapositive is both the converse and the inverse. We're going to switch them around and we're going to negate them. So it would be if not Q, then not P. Okay? And so these logical arguments are, well, they're just interesting, and we'll get some practice writing them today. But this is the foundation for essentially setting up your proofs later on. Okay. 1. Rewrite the conditional statement in if-then form. So we've got a statement, we want it as a conditional statement with a formal if and then part. So all pizza is good. There's a few different ways you could write this, I suppose, but I'm just going to say if a food is pizza, then it is good. So there we go. We have taken a normal statement and we've put it into a conditional statement with an if part and a then part. Make sure that you, at the very least, have those. Oftentimes we'll have just some sort of fun example, but then followed by a mathematical example. We'll follow that pattern here. It says 3 points are collinear. Remember what that was from chapter 1. If there is a line connecting them. So we'll say if 3 points are collinear, then there is a line that contains them. Pretty basic. Let's move to writing our converse, inverse, and contrapositive. So we've got it says if you are a basketball player, athlete. Just for fun, is this a true statement? So if you are a basketball player, then you're an athlete. But yeah, that's generally speaking a true statement. I think we could maybe come up with counterexamples of people who played basketball but weren't athletic. But let's just, for the sake of argument, say that all basketball players are athletes. Okay, the converse, we're going to flip them. So if you are an athlete, then you are a basketball player. So is this true? Well, I can think of a lot of athletes that are not basketball players. And so this converse would be false. The inverse. So we're going to take this original one and we're going to negate the if part and we're going to negate the then part. So we'll say if you are not a basketball player, then you are not an athlete. Well, is that true or false? You're not a basketball player, then you're not an athlete. Well, kind of for the same reasons above, I can think of basketball players who are athletes, or people who are not basketball players, but they are athletes. And so, yeah, this is a false statement. Okay, and with the contrapositive, we do both. We switch them and we negate them. So if you are not an athlete, then you are not a basketball player. Well, these ones are always tough. You've got the double negations going on, and it's really kind of confusing sometimes, a lot, to try to determine whether or not these are true or false. So I said earlier that the contrapositive is logical equivalent to the conditional statement. So I'm probably not even going to go through the mental hoops of trying to determine whether or not that's true or false. I'm just going to copy down what I had there. Okay, finishing up here with a biconditional. So a biconditional means that both the conditional and the converse are true. So the example that we did back here, definitely not a biconditional. I could not say that if you're a basketball player, then you're an athlete is true, and if you're an athlete, then you're a basketball player. So that was not a biconditional. Right? And so here in an example, we've got a statement that is a biconditional. We're going to write it as a biconditional statement. So we do this a little bit different. If a conditional statement was P if P then Q, okay, a biconditional statement is P if only if is the phrase that we use, Q. And the symbol that we use is kind of a weird symbol, but IFF is how I was taught to make that symbol. So write the definition of supplementary angles as a biconditional. So if we wanted to write it as a conditional, we could say if two angles add to 180 degrees, then they are supplementary. So this would be an example of how to write this as a conditional statement, if-then statement. Okay, and of course, because this is a biconditional, I could also say it the other way. I could say if two angles are supplementary, then they add up to 180 degrees. Okay, but we want to write this as a biconditional, which kind of says both in the same thing. So we're going to drop the if and the then. And we're going to kind of put a if and only if in the middle. So we'll say two angles add to 180 degrees if and only if are, and of course I could say it the other way as well. If two angles are supplementary, or two angles are supplementary if and only if they add up to 80 degrees. Okay, well, that takes us through conditional statements, and I suppose biconditional statements as well. Next time we talk, we'll be looking at deductive reasoning as opposed to inductive reasoning.